Today's topic is solving trigonometric equations. And, you know, doing these is not a whole lot different than when you were solving equations in algebra. We can apply algebraic properties to solving these equations. They're a form of transcendental equations, not algebraic equations. But we can solve them using algebraic techniques. This equation right here, in the end, our goal is to solve for theta. So the directions would be solve for theta. And when you're doing a trig equation, there usually is an infinite number of angles that will satisfy this. Therefore, many times you'll see a stipulation that says solve for theta between a region, between 0 and 360 or 0 and 180. We're going to do one revolution, so between 0 inclusive and up to 360 degrees, but not including 360 degrees. And so when we look at this, we're going to treat it like we would an algebraic equation. The first thing you want to do is you want to isolate the term that contains theta. Well, it's not just theta that you're isolating. You have to get the trig function that has theta. And so think of it like this. Think of this as being x. So if you were to solve the equation 2x equals a negative 1, your next step would be to divide by 2. And you would know that x is equal to a negative 1/2. And looking through that process, I know I haven't done anything that could cause extraneous roots. So that would be my solution. I could always plug it back in and double check to make sure that it did satisfy the equation. But kind of quick, simple, there we go. Going back and looking at this then, we can treat it like that. And instead of solving for x, what we're going to be doing is solving for the sine of theta. Okay, so our goal is to isolate the sine of theta. Well, first thing we need to do is, we don't want two sine of theta, I just want one side of sine of theta. So I'm going to divide both sides by 2. And then we have the sine of theta equals negative 1/2. So now we have to think about, okay, if we're talking about sine of theta, we're looking for angles that have a ratio of the opposite to hypotenuse that comes out to be a negative 1/2. And thinking about quadrants where sine is negative, we know that sine is negative in the third quadrant and the fourth quadrant. Both of those places will have a negative ratio. Then ask yourself, okay, think about when is the sine of theta equal to 1/2? When does it have a ratio of 1 to 2? And we know that occurs at how many degrees? And that happens to be the sine of 30 degrees is equal to 1/2. So we know that our reference angle is 30 degrees. So we start at 0 degrees and we rotate around and we go into the third quadrant 30 degrees. So this little angle right here, our reference angle is 30 degrees. So theta then is how far we've rotated from 0 all the way to our terminal side. And so we know we've gone 180 degrees plus an additional 30 degrees. So we know that theta is equal to 210 degrees. The sine of 210 degrees would be a negative 1/2. The other place we could fall is that the angle could rotate around and stop in the fourth quadrant. And when it does that, again, it stops so that its reference angle is 30 degrees. Well, think about this. We're going around and we stop 30 degrees short of doing a complete rotation. So in this case, theta is 360 minus 30, or 330 degrees. Both of those angles fall within 0 and 360 degrees. Those are the only two places where you will find sine equal to a -1/2 ratio. Now, if we took off this stipulation, there are an infinite number of solutions because we could continue to go around. We could say, make one revolution 360 degrees, plus then we could go another 180 and another 30 and stop there. That angle would also have a sine that was equal to a -1/2. But since we're only using this range, these are our solutions. Now going back through, we didn't multiply both sides by a variable or something that involved theta. We didn't divide both sides by something that involved theta, which we should never do. We haven't squared both sides. We haven't done anything that would cause extraneous roots. So, do you have to check? No. Is it a good thing to check? Yes, it's a good double check. So if we do a check, we have two cases. We have theta equals 210 degrees. I want to make sure that that is true. So I go back to the original equation, 2 sine, and I'm going to replace theta with my 210 degrees. Is that equal to a -1? Well, rewriting it in terms of its reference angle, we have 2 times the sine of 210 degrees. Well, 210 degrees again falls right in here. My reference angle is that 30-degree angle. And since we're in the third quadrant, we know it's equal to a negative sine of 30 degrees. And so we say a -1 times the sine of 30. Well, I know the sine of 30 degrees is 1/2. And 2 times the -1/2 is -1. And we have proved that we do in fact have a solution when we let theta equal 210 degrees. Our second check we're going to do is theta equals 330 degrees to see if that truly works or if I made a mistake along the way. 2 times the sine of 330 degrees. Is that equal to -1? Well, 2 times, and I'm going to write this in terms of its reference angle. Again, looking at where 330 degrees falls, right here, its reference angle is 30 degrees, and it's in the fourth quadrant, so it's equivalent to a negative sine of 30 degrees. Is that equal to -1? And we're back to the exact same point we were here, and we know 2 times a -1/2 is equal to -1, so -1 does equal -1, and I know that I will get this problem right. I have the solutions of 210 and 330 degrees.